Let's consider couplings next. The purpose of a coupling is to join two shafts together. There are several different types. There's a simple bolted type coupling, and I'll refer you to pages in your text 439 through 441 have some pictures. Well, really even 438 have pictures that you should look at. The simple rigid bolted coupling has just two simple halves that are bolted together, and the bolts are supposed to serve as the weak link. You don't want too many bolts. You really want the bolts to shear if there's an over torque situation. But it is a type of what's called a rigid coupling. Now, the issue when you're trying to couple two shafts together is there can be offset misalignment and angular misalignment. Now, another word for offset misalignment is parallel or lateral misalignment. You'll hear those terms thrown around. But of course, the issue is if you've got these two halves bolted together or somehow rigidly connected, and the shafts are, like this, you're going to generate very high stresses in the shaft material and the coupling, and it won't last very long as power is being transmitted through the coupling. So the offset and angular misalignment are two very important things. As a matter of fact, they're very expensive systems you can buy or rent that help in aligning shafts. And you see a sort of a cartoon version of it in the upper right corner of the slides. It's the system. A lot of times you have a laser and detector on one side and essentially a reflector on the other. And it turns out you mount these two rigidly to the two shafts, and then you actually rotate the entire assembly through 360 degrees, sometimes more than once. And what it does is it takes measurements of exactly where the laser bounces off and points back. It has a detector that detects the motion of the laser essentially, and from that and a little bit of math it can figure out exactly how much offset and how much angular misalignment the system has so that it can be adjusted. Now, another type of misalignment some people refer to as axial misalignment, and this is where the two aren't quite close enough to bolt together, but this system is not for axial misalignment. Most of the time what you do is you put the coupling together, you bolt it not tight but snug so that there can still be some movement between the two, and then you rotate through, and there's hardly any axial motion to consider there. But anyway, so with any type of rigid coupling, alignment is absolutely critical. And of course, you have to have some type of way to adjust either the machine or the motor. You can see in the lower left-hand corner a pump that's supposed to be coupled to a motor, and one of the two or both have to be adjustable so that you can get good alignment. Now, the nice thing about a rigid coupling is that it is very efficient at transferring energy, so you don't lose anything in the coupling, whereas flexible couplings can tolerate some misalignment, but energy is always lost in the flexible coupling, and it may not be enough to worry about. Many times it's not. There are many types. There's a bellows type. If you look on, and there's more than what I can go through here. I would really ask you to look at these pictures. On page 439 at the bottom, you'll see a bellows coupling, and it's just what it sounds like: thin corrugated metal, essentially, that as you turn it can flex and accept some misalignment, both angular and offset. There's also elastomers, so many different designs with rubber essentially for transmitting power. There's a chain type where essentially you have a double row set of chain and essentially two sprockets, one on each shaft. And then because of the play between the sprocket teeth and the links, and there's enough play in the chain that you can have some misalignment, both offset and angular. Now, more angular misalignment with the chain coupling. Universal joints are a different type of coupling. You may have seen these. You may have think of a drive shaft or a U-joint, you may call it. They're really called a Cardian joint, and they basically allow more than 3 degrees of misalignment. So talking about angular misalignment. If you only have a single one along the shaft, then you can only tolerate angular misalignment, no offset or lateral or parallel. But if you have two along the shaft, then you can tolerate a lot of lateral misalignment or parallel or offset, whatever you want to call it. I've included a video that shows some of the caveats about the motion of a double universal joint. It turns out if you still have misalignment between the ultimate input and output shaft, what can happen is a speed changing phenomenon. And so you might notice that on the front wheel drive cars, something called a CV joint is used, a constant velocity joint, instead of a universal joint. The reason for this is they want to make sure that no matter what the angle of the wheel is, that the shaft coming out of the transmission and the wheel rotate at the same speed regardless of that angle. So they're a different kinematic topology, if you will. Universal joints are common. They're used in rear drive, rear axle trucks. all the time. You know, they're used in heavy trucks. They're fairly bulletproof, but you just have to know what you're doing with them to use them well. Here are some photos, not from my experience. Most of my machine design experience is on the opposite end of the spectrum, in this very small area. I've designed a machine that literally could fit in a 1-inch cube, and it was a whole machine with, I think, 20 parts or something. It was just a small press fixture I made. Professor Dews, on the other hand, has designed very large shaking machines, as I've mentioned before, and so these pictures are some of his experience. So you see the double universal joints there, and probably my guess is that there's a splined connection at the center of that shaft on the left half of the photo, where those two can move in and out a little bit and have some axial adjustment. Here's some more drive shafts. You can see the size of the things here, how large they are, and then the weights they were driving, as well as the machinery back there on the extreme left-hand side that was driving it, the motors and things. Here's a close-up of a couple of the bearings and the offset weights, and I can see 4 universal joints here, as well as the grease lines for greasing all the bearings. Here's a nice close-up of one of the cardian joints on the left, or universal joints, with the bearing on the right and the grease lines. Now, turning our attention to seals, the purpose of a seal is twofold. A lot of times you're trying to keep a lubricant in place, but you're also trying to keep dirt and contaminants out. And there's many different types and many different purposes. There's, you know, many more materials can be used than what are shown here. There's many types of seals. Some seals are only used in certain industries. The shape of the seal can be different. And really the only thing you can do with seals is call a manufacturer. That's about all you can really do, unless you really dive in and you know a particular area, because I guarantee there's sealing in some other area that you don't know about. So this is where you really have to have an applications engineer's help in the particular field where you're trying to seal. Now, if you buy a bearing, for example, the bearing will have seals on either side of it to keep grease in place and, you know, keep dirt out. But of course there can be a variety of materials. Rubber, felt are used. There are different designs. A labyrinth seal is a different, you know, type of design. So there's many types. I've even included a video, a real good channel. They've not produced a lot, but they've got some really high quality stuff, where they talk about designing a groove for an O-ring. So you want to make sure you get the right amount of squeeze, and the information you need is in Machinery's Handbook, but they also talk about, I think they're called backup rings. I've used these before and designed with them, but I've got a backhoe and had to replace some seals on it. When I bought the thing, it wasn't really appropriate to say that the backhoe leaked hydraulic fluid. It would be more appropriate to say it hemorrhaged hydraulic fluid. So I had a lot of cylinders I had to take apart, order a seal kit for, replace, refinish and put back together. And O-rings are primarily what are used. Now they use backup rings so that the problem is there's always a little bit of space there, and it's possible the rubber with all the force can be extruded into that little bit of space. But watch the video, you'll see what that's all about. Anyway, the recommended compression and the recommended sizes and things for various O-rings is included in Machinery's Handbook. So that's something good to know. Another thing to think about, there's really two different ways to use a seal. Most seals are used where you're trying to seal a rotating shaft going through some wall, a housing or something. And either the seal can be made to ride on the shaft or be mounted rigidly in the housing. And so if you think about what that means, as the shaft rotates, if the seal is mounted on the shaft, then it has to move away from the shaft, right? So it has a larger diameter than the shaft. What that ultimately means is that seal is going to have a higher surface speed than if the seal is rigidly attached to the housing and the shaft simply rotates inside of the inner diameter of the seal. So you end up with a lower surface speed. So one of the difficulties is, even in installing a seal, you can damage it. You've got to have the right material. Another huge thing is that the seal has to be compatible with the local environment, whatever it happens to encounter in terms of temperature, dirt, wear, abrasion, whatever, vibration, and it has to be compatible with the chemical makeup of the oil. Oil is not a simple thing where we just pull it out of the ground and throw it in the engine anymore. There are tons of additives, there's synthetic oil, there's different things included in oil, and if you don't get the right sealing material with whatever it is you're trying to seal against, the seal is going to degrade very quickly, because it's a very stressful environment, I should say, to the material. And of course there are seals that have springs inside of them to help hold the sealing material against the rotating elements. And so again, this is an area where probably more than just about any other area you really need help from the manufacturer that makes seals, whoever you buy them from. And there are multiple manufacturers for many different types of seals and areas. Here's an enlarged view of a bearing seal, and you can see that typically you have a seal on both sides. Now sometimes you can get bearings with a seal on one side, and the idea is that inside of the housing there's going to be oil that mixes in with the bearing as well. Some bearings, of course, are just pre-greased and you let them go, like on your car, right? There's a dust cover and things, but nothing to really keep nasty stuff out. If you have a rear-wheel drive car and you replace the taper roller bearings in the front wheels, there's a little cap that it's basically made out of sheet metal. You have to pry off, and then you have to tab it back into place, and it's supposed to help seal the bearing. But there are multiple different ways. A lot of times a seal doesn't necessarily have to be well, it has to be attached to one or the other. It has to be attached to either the rotating element or to the housing, and there has to be some seal between those two. So I don't know what else to say. I feel at somewhat of a loss because I feel like I haven't told you much about seals. Just basically, you need help, and maybe that's the best thing that you should know.